this one is going to be more side by side using commands in the notebook as well as the UI together. So we're going to look at a near spec IFU data cube. And we'll just do some aesthetic things, rearranging viewers, using API hints. And one of the new features of Jdaviz is using the data quality flags, which comes from the JWT calibration pipeline. And at the end, we'll get to doing some actual analysis with the emission lines that we see in the spectrum. So first thing we're going to do is just import all of our necessary libraries. We're going to need AstroPy and specutils. As Claire showed, we're going to import Jdaviz as JD. And so now we can set up our data, and we're going to do this from the notebook. So this galaxy that we've chosen comes from the Alpine Crystal JWT survey, which is a near-spec follow-up of a group of high redshift dusty galaxies originally detected by ALMA. This one happens to be an AGN host galaxy, which we will get to the significance of that later. But if you want to know more about this particular sample, you can go to the survey paper. And in there, we can find the proposal ID, the PI name, and anything else that would help us search for these files on MAST. So I have the MAST file for you where we've chosen this particular galaxy, but it can always be helpful to go to MAST if that's what you're looking for. So we're going to load in our data set with jd.load. We're going to enter this URI, and importantly to the new version of Jdaviz, our deconfigured version, is this format argument. So we need to tell it that this is a 3D spectrum. So if you use the old version, you might have done like cubeviz.load, but here we can just use the big application and specify the format. So I'm going to load that, and this is going to download the file. I happen to have it cached already on the platform, but you should see a message saying that this is downloading. I'm going to show a different method for showing our actual UI window, and I'm going to use Sidecar, where Claire used the pop-out. With Sidecar, this will open up a side window. Do note that this only works in Jupyter Lab and not Jupyter Notebook. So if you can't get it to work, that could be the reason. So here we have our Sidecar window, and we see 3 viewers pop up. So at the top here, we have our flux cube, the actual data in grayscale, and the data quality layer is these colorful pixels behind it. In the middle, we have the uncertainty cube, which is coming directly from one of the FITS extensions. And then this bottom viewer, the 1D spectrum viewer, is automatically extracted by Jdaviz. And so this is a 1D spectrum that is collapsed over all of the spaxels in the cube. So I'm going to make some more room here. I'm just going to click and drag up here. It's a little confusing that the grayed out one is the one selected, but I'm just going to make sure I'm in 3D spectrum so I can see my flux cube. And so we can talk about the data quality flags. As I said, that's the pink and purple pixels here. And so this is, again, coming from the JWT calibration pipeline. It's a data quality mask that will flag pixels that are unusable for whatever reason. So the values are integers, and it gives you a bit mask array. And we can find out some more information by going to the plugins menu up here and clicking on data quality. So our science data is the cube that we loaded in. And if we scroll down here, I'm just going to make this a little bit bigger. Okay, well, it's a little squeezed in the sidecar, but we can see that the red pink color corresponds to 0, do not use, it's a bad pixel, and the purple corresponds to non-science. So this is just outside of the spatial coverage from the IFU, so that's all the purple means. By default, the spectrum will load into the middle slice. And we can see by this vertical bar here that it is, again, centered in the middle of the cube. But this is sort of a featureless part of the spectrum. We can't really see much information about the galaxy. So we are going to change the spectral slice with the spectral slice plugin. So over here, back to the notebook, we can access the API we can access the API using the plugins here. So jd.plugins, we're going to access spectral slice. This open in tray is not a necessary part of actually doing the analysis, but it can help you when you're using this side by side. It's basically just going to open up my spectral slice plugin over here. I see we have a raised hand in the chat. Maybe one of my colleagues can answer that on Slack. Okay, so we have opened this up, and we're going to set the value to 4.38. This is in units of microns. So I've done that already, and so now we can see that this vertical bar is centered on an emission line, and so we see the bright components of that galaxy. So next we're going to do some model fitting. So coming from the science of high redshift galaxies myself, it is so exciting to see near spec spectra of high redshift galaxies, because look how beautifully deep this is. We have very high signal to noise continuum here. But if we want to do some analysis on the emission lines, the first thing that we would want to do is actually subtract out that continuum. So we're going to call now a different plugin. We're going to go to model fitting. Once again, we're going to do this open in tray so that we see it show up over here in our sidecar. And if you're curious about everything that's going on here, all of the available options, this dir command will help you access all of the available options. And so some of them are going to be things like setting the model component, calculating the fit, and then some of them are going to be things that are returned by your model fit. If you are totally lost and you're not sure how to set this up in the notebook, we can go over here to the upper right to toggle the API hints. And now in blue, we see all of the ways to sort of set up these different plugins and how to set the options. We'll get to that in the next part of the tutorial. I'm going to turn this off for now, but it's just helpful to know that that's there. Coming back to the model fit, the necessary parameters to set is going to be selecting our data set. We want to select that 1D extracted spectrum, and so that has the original file name minus the dot fits, and then in parentheses sum. And then we're also going to set our spectral subset. We only have one. Our subset is the entire spectrum. Like Claire was mentioning before, we can define subsets spatially and spectrally, but I haven't shown you any of those, so the only option is entire spectrum, but we will set it nonetheless. We're going to fit this continuum with a spline 1D model, and we're just going to label it S just to keep it simple. So we're going to define our model component and then create the model component so that Jdaviz knows that that's what it's going to look to fit. And if we scroll down here to model components, we can see that we've chosen spline 1D and that, well, it has the label S1 in here. Now we want to fit only our spline 1D component, so we have to give it an equation. And there are many different combinations of things you can fit. You could do the emission line all at once. You could fit Gaussians, whatever's relevant to you. And you can see in the drop-down menu from model component all of the available options. But we have a very simple equation. It's just going to be S, and we're going to label it continuum model so we can keep track of everything. And then we will calculate the fit, and add data equals true means that the application will keep track of our data and allow us to see it in the viewer. Okay, so that fit was successful. We see it in the blue line here. It's not super visible, so we can go over here to plot options. So again, we're going to go up to settings and options up here, plot options. We will select our viewer, and in this case, it's 1D spectrum. And so here's our data menu, similar to over here on the right, but it is showing us what is currently being displayed in the viewer. So we have our 1D extracted spectrum and the continuum model. So I can play with the plot colors. I can make it bright green if I want. I can play with the line width, whatever might be aesthetically nice for you to save for your science. Coming back over here to the notebook, we can see that it returned all the coefficients of that spline 1D model, the spectrum object, and it has the redshift set to 0. We will return to that important point in a few moments. But continuing on with this model fit, we're going to subtract it and add it to Jdaviz. So this is very simple. We will simply subtract it. So our science data is under our data sets. And again, it's that 1D extracted spectrum. And .getData will retrieve the spectrum object and give you the actual data that is stored in there. The model data is also stored. We called that continuum model. And then our continuum subtracted spectrum is simply science minus model. So that is in our notebook, but now we want to load it into Jdaviz. And so we can call this again jd.load. We're going to load in our continuum subtracted spectrum. This time the format is a 1D spectrum, and we will give it an informative label. And we can see that it showed up over here in our data menu. We also see it in the plot options. And I don't like that it gave me a second bright green. We'll make it bright purple. And you can't really see it, right? So it's down here. And it's sort of, because we have subtracted the bright component, it's not super visible. So we can toggle the visibility of the different layers by accessing the data menu. You can do this in the API. You can also do this by clicking on the eyeballs here. We still can't see it, right? It was super faint. I will make a little bit more room here. And we can auto scale the flux by hitting the home button. It will reset the zoom. And now we see our beautiful continuum subtracted spectrum. The last thing we'll go through here is the line list plugin and how this could be helpful for fitting an approximate redshift. So this is not going to be like a numerical solution for your redshift, but it could be helpful to line up emission lines and get sort of a a ballpark estimate of a redshift if you have a high redshift object. So one last time, we're going to open the plugin in Tray. This is going to take us down to our line list plugin. If we scroll down to preset line lists, there is a number of available line lists that contain things that you might want to plot. And so I know that this is a rest optical spectrum of a galaxy, so I'm going to select galactic optical range, and I'm going to load that list. So over here in Salmon, we see all of the available lines if I click that drop-down menu. There's many lines that are possible, and they are all set not to be visible at first. So I'm going to choose a few that I want to plot. You can use the search button since there's so many options, and it doesn't want to. Oh, there we go. Okay, so I'm going to choose H alpha, H beta, a helium-1 line. Okay, and we're going to do the 5875 line. Turn that on, and I'm also going to do the forbidden 03 doublet. So when you search, you'll need the brackets and the space between the atomic species and the transition. So I'm going to turn on 2 more 03 lines. We're going to do 4960 and 5008. Okay, so what I would have expected is that these all get plotted on our viewer and we see nothing. But we do see this gray triangle over here, and that is indicating that all of the lines that we chose are way out of the spectral coverage of my present spectrum. This is sort of hidden in Sidecar, but these are in units of microns, and I've chosen these rest optical lines that are bluer than the infrared spectrum. And that's because this is a highly redshifted galaxy. So we can find the redshift if we scroll back up to our line lists, we're going to see this submenu in Redshift. When you have more room on your screen, there's a slider here, and you can move the redshift between plus or minus 0.6, but spoiler alert, this galaxy is much higher redshift than 0.6, so I can directly give it a redshift. It happens to be somewhere around redshift 5.5. If I put in 5.6, I see that the lines show up, but they're not quite lined up with where I see emission lines in the spectrum. So I can move this around a little bit, again with the slider, but I do happen to know that it's at 5.67. And so now I see these red lines match up perfectly with my emission lines. So that's what I mean when I say that it's sort of an approximate guessing game, but you can look at all of your high signal to noise lines. But maybe I'm not familiar with optical spectra of galaxies and I don't know what line is what. I can't remember their wavelengths. We can solve that problem by enabling the line selection tools. And now this top menu is going to change to spectral line selection. And if I click on these vertical bars here, select or identify spectral line, this now makes these vertical red lines clickable. And if I scroll back up to identified line, I know that I clicked on H alpha. So that is the end of what we'll do together, but there are some bonus exercises in this notebook that may be helpful if these are the types of objects that you study. We showed you how to fit the continuum. You can also fit your emission lines, and you can do multiple components. So I told you that this was a high redshift galaxy with an AGN. And if you're familiar with AGN, you may know that, let's see. Well, I'm having trouble scrolling or zooming in, but you may know that there would be multiple line components. And so maybe I wanted to fit a broad Gaussian and a narrow Gaussian. We can do that here with the model fitting plugin. And another thing that may be relevant to your science is creating moment maps. So currently Jdaviz can fit moment 0, 1, and 2 for a flux map, a velocity map, and velocity dispersion, and that is in our moment maps plugin. So you can feel free to run through those cells on your own, mess with your parameters, fit the line as you see fit. But I'll end there.